This lecture is electrical wiring installation. We will provide an overview of the requirements for electrical installations in domestic and industrial settings, as well as some examples of good practices and principles of electrical installation. The coursework for this topic is the handout Basic Electrical Installation Work, which I have shared as a PDF on the portal. So first off, the most important aspect or the reason why we have electrical installation work carried out is generally to provide protection and to supply consumers in a safe and useful manner. The electrical installations allow the installation and the usage of electrical devices in such a way that human beings are protected. So the key element that must be taken care of when carrying out installations is the safety of users. And there are two main types of safety. You have basic protection and you have fault protection. Right? Basic protection means that you are protecting human beings from getting into contact with electrically charged devices, that is, directly touching electrically charged devices. In the event that a person touches an electrical charged device or component, they are likely in the event that a human being touches an electrically charged device, they are likely to experience an electrical shock due to an electric current flowing through their body. And the main damage that can be caused is to the nervous system. So the nervous system makes use of signals that electrical signals, and the cells that form the nervous system can experience serious damage if they encounter a voltage that is higher than 50 volts. So basic protection is achieved through insulation or enclosures. That is, you provide a physical separation between the electrical conductors and the human being, either through insulation, such as with wires or cables. Those usually have plastic PVC sheathing or asbestos or paper sheaths that cover the entire length of the conductor. Enclosures usually consist of panels or boxes that enclose the electrically charged devices and prevent access from human beings who may touch it accidentally or due to lack of knowledge. Fault protection, on the other hand, is protection against indirect contact. So in the event that there is a short circuit, that is, a live potential carrying conductor comes into contact with either the body of a device, the metallic body of a device, or there is a fault between a live wire and, say, the earth or the neutral, you would require fault protection, whereby this prevents human beings from touching devices that are electrically charged. Fault protection is usually provided by earthing, in which case you have a system of wires that will provide an easier path for electricity in the event of a fault. They will provide an easier path than the human body. So earthing wires are copper wires that run along the length of a whole installation and give this alternative path to electricity in the event of a fault. At the same time, in addition to safety, you can also have protection for the electrical appliances and devices. Yeah, this is in the form of overcurrent protection or over voltage protection and various other types of protection, high frequency, low voltage, and so on and so forth. This prevents damage to the devices themselves by disconnecting supply before they burn out or suffer any kind of damage. Right. So let's look at some of the other aspects of electrical installations. So first off, let's look at three-phase installations or three-phase supplies. These are commercial supplies, and they are used in factories, industries, large buildings, institutions, hospitals, and so on and so forth. So what is being shown on the screen right now is the electrical distribution or the supply point through which electrical supply is provided to a three-phase installation. So what will happen is right here at the bottom, you have L1, L2, L3. These are the supply points through which electrical power is provided to the circuit, right? First off, at this point, let me just zoom in. So at this point, you have your three phases. So usually those phases will be, they are designated red, yellow, and blue. And throughout the installation, you will see indications of those three colors, codings for the three phases that are supplied. Once you have your supply connected, you will then have a series of connection points. So here you note three thick copper bars that are connected to various takeoff points. So these three copper bars, each with one phase, so this is red, yellow, and blue, each phase has been connected to various points along this. This is called a bus bar. The reason for that is you will have this set of bus bars, for each of the phases, the red phase, the yellow phase, and the blue phase. Each of these bus bars is connected through these breakers. We call these MCBs, miniature circuit breakers, miniature circuit breakers. And these provide a means of connecting across to the various load circuits. So at each of these points, you will have a circuit that is connected within the building that is housing this distribution board. So these circuit breakers will then provide a path through which electrical current will flow to the various circuits and devices that are connected. Note that these are only connections to live wires, so red, yellow, and blue. The neutral wires are these black ones that are indicated here. So the neutral will have its own bus bar indicated here, and you can see the word neutral written next to it. So those neutrals will have various points at which you can connect now to circuits. So for every phase that is connected, you can tap a neutral from any of these points. These are screw heads. So you would have your conductor being connected here, and the exposed part of the head is tightly connected to that bar. The neutrals are exposed because you do not need insulation, as the neutral provides a return path. generally you'll note that breakers and protection devices are only applied to the lives or the phases themselves. Neutrals do not require such protection. You will only find switching at the point of incoming power. So you will also see here, while we had the red, yellow, and blue phases coming through your main breaker or your main switch, your neutral will be connected on the side through this connector, okay, and then tapped through various points. You can see as you follow along the black wire, it goes in here, through here, and connects to the two sets of bus bars. On this other side, you have the earth connectors. So all circuits will leave the distribution board with a set of live, neutral, and earth. So the earth wires are all connected from here as they pass to the circuits. This point is connected to a physical earthing rod located somewhere in the building that connects directly into the ground. Usually this is a copper bar that is sunk deep into the ground with usually kept wet so that there's good conductivity with the right. So that is three-phase distribution. Okay. Breakers on the live, miniature circuit breakers, and various incoming points. So let's move on to single phase or domestic power supply. So this is a different kind of supply whereby the customers are connected straight to single phase. They do not receive three-phase power. So that will look like this. This is a schematic diagram of this kind of connection. So generally what you will notice is you have from your utility supplier, they will tap a neutral and a phase, or in other words, this is called a phase or a hot or live or line. These are color coded. So throughout the building wiring, you will have brown representing the phase wires or the live wires, and blue representing neutral. The green and yellow are the color codes for earthing or ground wires. So similarly to what we had before, your neutral and phase would go through the energy meter, which is owned by the utility, Kenya Power or whoever it is. From the energy meter, it will cross now into your first point of entry. So at this point, beyond this point, this is now the customer's side. Equipment on this side belongs to the utility, for example, KPLC. Right? So now crossing over into the customer side, you first have a double pole. DP stands for double pole. We'll talk about that shortly. A double pole MCB, we already know that is a miniature circuit breaker. So these MCBs are set, or they are devices that sense faults and will trip the circuit and open it so that it is disconnected from the power in the event of a fault. So from the double pole, you have your neutral going straight to the bus bars, similar to what we saw for three-phase, and your live will connect to a common bus bar over here, from which you connect a series of single pole MCBs. So these single pole MCBs provide protection for individual circuits. So each of these lines forms a circuit to various devices within the building. Okay, so these can be lighting, sockets, heating, cookers, and so on and so forth. Similar to the three-phase, you will still also have your earthing circuit. The earth here, this symbol represents the connection to earth rod, right? It's a physical connection to the earth. And each of these wires, color-coded yellow and green, is connected to the bus bar there. This entire box, I can call it, is called the consumer unit, and it houses all the breakers and connection points for the circuits that are provided across the building. So from here you can have lighting circuits, you can have socket circuits, you can have hooker circuits, and you can have heating or boiler circuits. So let's talk about each of these in turn. We'll start with a bit about lighting circuits. So when we talk about lighting circuits, there are generally some accepted norms that we have. Usually when you have a lighting circuit, you will generally have 7 to 8 lighting points, depending on the type of circuit, but there's a large variation of what you can have, either LED, fluorescent, and so on and so forth. We will go through this in a topic on lighting. These are usually thin cables, so 1.5 mm squared or 2.5 mm squared. And you would have parallel connection such that you have lights being connected, looped from one point to the other, which is the most convenient way of doing so. Yeah. So in the key, so when you have lighting circuits, the main key aspect of lighting circuits is switching, which we will now look at the next few slides. So first of all, you have one option, which is your one-way switch wiring. So in this case, you have a neutral. CPC is earth, that is the called CPC is the circuit protective conductor, or simply put, the earth, which is yellow and green. So this is the general wiring circuit that you would find for a simple lamp with one switch, or lamp circuit with one switch. You'd have your source at this end, from where you have neutral, earth, and live, with the blue, brown, and green and yellow. They would all connect at a junction box. So from here, you have your earth splitting and connecting to your one-way switch. However, the live is, the switch is connected directly to the live circuit. So you would branch off to the live. So your circuit looks like this. You branch off to the live. You have your switch. It goes back to the junction box and onwards to the lamp. Once it is through the lamp, it travels through the junction box and back to the source. So you then have the flow looking like that, right? The forward path through the load and the return path, right? Now, when we talk of lamps and circuits, you generally would have this. Here we are having one lamp, but from here you could then loop to a second lamp, and you would then further loop to a third lamp, and so on and so forth, as many times as you require, within the limits, of course, of the carrying capacity of your circuit. Okay, this is a simple one way, one switch, one set of lights. So anytime the switch is activated, the lamps would go on. If it is switched off, the lamps would go off. But in some cases, you would want to have more than one switch. So here we have a two-way switching diagram. So your circuit looks like this. So let's redraw it a bit. If this is a live wire, it would first encounter a switch, one switch like this, right? Notice that it has two connection points. We call it two throws, okay? It can either be connected to here or it can connect to here, which is what we've indicated on this point. And the connection around this junction box can be simplified to look like that, right? So you have two lines. These are still live, but you have provided two possible paths through which circuit can flow, okay? Then from there, it goes to your lamp. And then, of course, it travels back to the neutral. Not coming into contact with each of them. So what now we would find is that you could then have two possible paths. So the first path would be through here, 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 and to the lamp. Okay. Now, if we switch any of these switches, if we switch this one, you would then have it switching here, and you disconnect from this point. So let's say here, right? So you have it switching to here. That means that if your path is through here, you now have a disconnect at this point, and your lamp will not come on. It is off. You switched on switch number 1, and the lamp has gone off. If you switch number 2, which would be like this, if you do that switching to here, you once again now have a complete path, so your flow would continue, right? So that means that in this configuration, either of the switches can actually provide a switching mechanism for your lamp. And that is why we call it a two-way switch, because it can switch between two sets of lamps. If we want to add more to your switch, we want to have more than two switches switching the circuit. We would then use an intermediate switch like this. So this type of circuit now allows you to have more than two switches in any given point by using the configuration that I will show here. So here you have several switches. So here you have several switches. Switch 1 and 4 are two-way switches, such as these ones, and switch 2 and 3 here are intermediate switches, such as B. The intermediate switch switches either in this direction or in the parallel direction. So it interposes the wires. So if the path was coming through here, and it encountered an X configuration, let me just clean that up a bit. So it encountered an X configuration, such as this, X like that. It would mean that your path would continue through here, through here, through here, all the way to the lamp. So you have one continuous path all the way to the lamp. But if you were to switch any of these switches, so like for example that one, you switch it to the parallel position, it would flow through here but stop at this point because there is no path. The path is disconnected. It has now left the path that was closed in this point. The two are separated from each other. Okay, so any of the four switches can actually provide a means by which you would switch from you would switch on or off your circuit. In addition to lighting circuits, we then have radial or rather socket circuits. These are directly connected from your source or from your consumer unit through fuses depending on the amount of sockets that you would need. So for example, if you have a large floor area, you can have several sockets connected in parallel to each other. So here, what it would actually look like is you would have your three sockets or your three cables being connected to each point within the socket. So you have your earth, your live, and your neutral, right? Then from here, they are connected to the next socket. So you have there, and there, and so on and so forth. So you essentially have wiring looping from one socket to the other, which is what we have represented with a single line on here. The size of the fuse and the thickness of the cable is represented by the amount of sockets that you would have. It is commensurate to the amount of sockets that you would actually connect to the circuit. If you need more sockets, you would have a higher fuse because you're likely to have higher current flowing through. If you don't need as many, you can afford to have a thinner cable and lighter sockets. An alternative configuration to the radial circuit is the ring circuit, which then provides a path back to the initial circuit. Okay, remember that these are actually three wires going through. So whereas the return path is being provided by connecting your appliance, whatever it is, it is complete in itself. But the ring, the advantage of the ring is that it closes the loop and provides a redundancy of the socket circuit itself. Apart from that, we have water heating circuits, which are connected to boilers, and we also have cooker circuits, which are connected and have high ratings. So to finish off, let's look at some of the types of cables that are used with various wiring types. So here are various wiring systems. One of the most common systems is PVC sheathed or armored cables. So these are generally used for lighting and socket circuits. The reason for that, they are easy to pull through buildings. They are insulated, they are flexible, they are easy to lay for circuits that are less prone to damage and so on. They can be self-contained. Another type of wiring is the conduit system. This is more common in heavy-duty systems. You can make use of steel conduits or PVC, or you can have an alternative of flexible conduits, which are generally used in areas which require which have inconvenient positionings. These types of wires are more, or these types of systems are more heavy duty and can be used in environments where it is not possible to go through the building itself, or there are areas where there's likely to be damage, such as outdoors or in roofs and so on and so forth. In addition to conduits, you can sometimes have trunking systems. These are related to conduits in that they provide mechanical protection of the stranded cables that are passed through them. And finally, we have cable trays. This is a system of installation where you're not likely to require physical damage, or there is not likely to be any physical damage encountered or tampering from people. This is usually found in industrial settings, whereby you are fairly guaranteed that they are in a position that laymen will not tamper with them, so they are fairly safe. And this allows for easier maintenance in that you can lay them out and they are physically visible to any service personnel that would need to make use of them, or would need to change the system itself. So that's an overview of electrical installation, electrical wiring systems. This is a key part of electrical, providing the system that will enable us to consume electrical power. It forms one of the elements of electrical systems as indicated.